The next set of queries we'll show introduce the concept of aggregation in SQL. Once again, we start with the basic select from where construct, and this time we're going to introduce what are known as aggregate or aggregation functions. These are functions that will appear in the select clause initially, and what they do is they perform computations over sets of values in multiple rows of a relation. And the basic aggregation functions supported by every SQL system are minimum, maximum, sum, average, and count. Now, once we've introduced aggregation functions, we can also add two new clauses to the SQL select from where statement, the group by and having clause. The group by allows us to partition our relations into groups, and then we'll compute our aggregate functions over each group independently. The having condition allows us to test filters on the results of aggregate values. The where condition applies to single rows at a time. The having condition will apply to the groups that we generate from the group by clause. All of these constructs will become very clear when we show some examples. As usual, our examples will use our simple college admissions database that has a table of colleges, a table of students, and information about students applying to colleges. As usual, we have 4 colleges, a bunch of students, and applications of students to colleges for specific majors. Our first aggregation query is a very simple one that computes the average GPA of the students in the database. Here's the query, but just to explain the query, let me first replace the aggregation with star. When we run select star from students, we get a result here. Specifically, when we look at the GPA column, what the aggregation is going to do is perform a computation over all values in the column and then produce just one tuple in the result that has that value. So we'll write average GPA. We'll run the query, and we see now the average GPA in the database. Our second query is a bit more complicated. It involves a join. What it finds is the minimum GPA of students who have applied for a CS major. So we do the join of student and apply on student ID, filter for major equals CS. Once again, let me just remove the aggregation first so we can see the result without aggregation. Here we see all of the information about students who have applied to a CS major. The aggregation is going to look at the GPA column, and it's going to take the lowest value in that column. So we write min GPA, run the query, and we discover that the lowest GPA is 3.4. Now let's go back to the average aggregate function again. So let's compute the average GPA of the students who have applied to computer science, run the query, and we see the result is about 3.7. In fact, this result is probably not precisely what we were looking for. In a previous video, we talked in some detail about this particular form of query versus using a subquery to find the GPAs of students who have applied to CS. The issue with this particular query, and let's go back to the select star version, is that if a student applied to CS multiple times, for example, student 123 Amy applied to both Stanford and Berkeley, then when we compute their average GPA, we're going to be counting their GPA twice. Presumably what we actually want is to count the GPA once for each student who applied to CS, no matter how many times they applied. So in order to do that, we use the subquery form where we select from student, and then we just check for each student whether their ID is among those who applied to CS. So let's just do a bit of editing here. From apply, where major equals CS. I'm not a very good typist. Let's just first take a look at the subquery form. And we see that we made a mistake here. And it says that we forgot a word here, which is in. Apologize for that. OK, now we have the students who applied to CS. And in this case, we only have one instance of each student. So now if we run the aggregation, when we compute the average GPA, we'll correctly count each student's GPA only one time. So remember, it was 3.7 approximately before. Now we run the query, and we see that the correct result is 3.68. Not that different, but this one is the numerically correct result. So far, we've seen the average and min aggregate functions. This query shows the count function. So not surprisingly, the count function just returns the number of tuples in the result. So this particular query finds the number of colleges in our database whose enrollment is greater than 15,000. Just to be thorough, let's run the query without the aggregate function. And we see that there are 2 of them, and the aggregate function simply counts those number of tuples. We run the query, and the result is 2, as expected. let's do another count query that looks very similar. In this case, we're counting the number of students who have applied to Cornell. So the query looks the same. We'll run the query, and we discover 6 students have applied to Cornell. Well, in reality, what we've actually counted is the number of applications to Cornell, not the number of students who have applied to Cornell. If a student applied 3 times, then we're counting them 3 times in this result. So in some sense, this is similar to the previous one we saw where we were overcounting, and we could try to fix it with a subquery in the in and so forth. But actually, SQL provides a very nice way for us to perform the query that we want. In the count function, we can put a special keyword distinct and then the name of one or more attributes. And in this case, what the count will do is we'll look at the result, and then it will count the distinct values for the particular attribute. So we run the query, and we find that there are 3 distinct student IDs. If we ran it without, just like this, when we see, we would look, and again, we would find that there are 3 distinct student IDs. So count distinct actually turns out to be a very useful feature in SQL. Here's a rather complicated looking query, and I have to admit it computes something fairly obscure, but it does demonstrate some features. What this query computes is it gives us back all students where the number of other students who have the same GPA as the student is equal to the number of other students that have the same high school size as the student. Again, I admit it's a little bit obscure, but let's take a look at how it works. So it looks at the student relation, and for each student, it counts the number of other students, that's by testing that the ID is different, that have the same GPA. It also counts the number of other students that have the same size high school, and if those 2 values, and these subqueries both produce a single value, which is why we can test equality, if those 2 values are the same, then the student comes out in the result. Let's run the query. We get our answer. I'll leave it to you to verify by looking at the data that this is indeed the correct result. Here's another complicated looking query, although this one computes something quite a bit more intuitive. What this query computes is the amount by which the average GPA of students who apply to computer science exceeds the average GPA of students who don't apply to computer science. And we're going to assume it does, in fact, exceed. So we're using, in this example, subqueries in the from clause, which I hope you remember from the previous video. A subquery in the from clause allows you to write a select from where expression and then use the result of that expression as if it were an actual table in the database. So we're going to compute 2 subqueries in the from clause, one of them which is the average GPA of CS applicants, and one the average GPA of non-CS applicants. Let's look a little closer here. So this query here says let's find the students who have applied to major in CS. Let's compute their average GPA, and we'll call it average GPA. We'll take the whole result, and we'll name it CS. Similarly, the second new relation that we're computing in the from clause computes the average GPA of students who did not apply to CS. So their student ID is not in the set of students who applied to CS. We'll call that one non-CS. So now with this from clause, we have a relation called CS with an attribute called average GPA, and a relation called non-CS with an attribute called average GPA. And in the select clause, we'll simply do the subtraction of the non-CS GPA from the CS GPA. We run the query, and we discover that the CS applicants exceed, on average, the non-CS by 0.19. Now, just for demonstration purposes, let me show that we can write this same query by using subqueries in the select clause. You might remember from the previous video that in a select clause, we can write a subquery as long as it returns a single value. We're going to go even further. We're going to write 2 subqueries that return single values and subtract them. So I'm going to replace this from with select. I'm going to take out this whole first line here. And then I'm going to, let's see, what else do I need to do? I'm going to take out the as here, and I'm going to replace it with a minus. I'm going to take out the as here. So now what we've got is we've got the average GPA of CS students in the select clause producing a value. The average GPA of non-CS students, we perform the subtraction as part of the select clause. The last thing we need is something in the from clause, so we'll say from student. We'll call the result of the subtraction D, let's say, for difference. We run the query, and we get almost the same result except for a bunch of duplicates. The reason for the duplicates is that we computed this result once for each tuple in student. We can add distinct, and now we get the single result. Now let's learn about the group by clause, which is only used in conjunction with aggregation. Our first query is going to find the number of applicants to each college, and it's going to do so by using grouping. Effectively, what grouping does is it takes a relation and it partitions it by values of a given attribute or set of attributes. Specifically, in this query, we're taking the apply relation and we're breaking it into groups where each group has one of the college names. So there'll be the Stanford group, the Berkeley group, and so forth. And then for each group, we will return one tuple in the result containing the college name for that group and the number of tuples in the group. So to illustrate what's happening with grouping very clearly, let me start by replacing the select clause with select star, removing the aggregation, and doing an order by on the college name. So that just illustrates the groups that we're going to be using in the actual query. So we see there are 3 tuples for Berkeley, there are 6 tuples for Cornell, and so forth. Within each group, then, for the particular query we're doing, we're simply going to count the number of tuples. So going back to the group by form, we return the college name, and we return the count of the number of tuples. Now, before I actually run the query, one thing to notice is what it makes sense to put in the select clause here. We're grouping by the college name, so the college name is going to be the same for all of the tuples in the group. So it's sensible to include that, but it wouldn't really be sensible to include one of the other attributes that differs, although we'll see an example later where we include that and interesting things happen. For now, we'll just put the name of the grouping attribute, and then we can perform aggregation over that, in this case count. We run the query, and we see that there are 3 applicants to Berkeley, 6 to Cornell, and so forth. Here's a very similar query, just as a second example. In this example, we're finding the total enrollment of college students for each state. Now, we only happen to have 3 states and 4 colleges in our database, but what this query does is it takes the college relation, it breaks it up into partitions by state, and then within each partition or group, it will return the state for that partition and the sum of the enrollments. We run the query, and we see the expected result. Here's a more complicated group by query. In this case, we're grouping by 2 attributes. We also have a join involved, and we're going to compute 2 aggregate functions in our result. What this query computes is for each college and major combination, the minimum and maximum GPAs for the students who have applied to that college. As usual, before we do the aggregation, let's replace the query with one where we can see the groups explicitly. So I'll put GPA here, and instead of grouping, I'll order by. And we run the query, and we see for Berkeley Biology, we actually only have 1 applicant. For Berkeley CS, we have 2. I think Stanford CS has the largest number of applicants at 3. So once we put the aggregation back, each of these combinations of college and major is going to be considered individually, and for each one we'll compute the minimum and maximum GPA. So let's go ahead and do that. All those parentheses. Okay, change this to group by, run the query, and here we see for Berkeley Biology the minimum and maximum is the same because we saw that there was only 1 student who applied to Berkeley Biology. Stanford CS we had 3. We can see the spread of their GPAs and so forth for each college major combination. Now, what if we were interested in finding information about the spread of GPAs for each college and major, what the difference is between the minimum and the maximum? So let's suppose, in fact, what we wanted to find was the largest spread, but let's take that in steps. I'm going to take this current query here, and I'm just going to slap it into the from clause. So now, in the from clause, I'm going to have a relation, we'll call it M, that's going to have the college major combinations and the minimum and maximum GPA. This M is going to now have the result that we see below. Now, once we have that result to work with, in the select clause, we can access the attributes here. Let me call this one MN and this one MX. And if we write just MX minus MN here, what we're going to get is a list of the spreads of the min to max GPA for each college and major. So we see many of them are 0. Those are all of the combinations that had just 1 student, but in some cases we actually have a spread. If what we want to find is the largest spread, watch this, it's very cute. We just simply put a max function right here, run the query, and we find that the largest spread between min and max is approximately 1. Our next sequence of queries introduces some subtleties of the group by clause. What our query finds is the number of colleges that have been applied for, the number of colleges that have been applied to by each student. So the query joins student and apply. It groups the result for the student ID, on the student ID, and then for each student ID finds the number of distinct colleges in that group. So once again, just to illustrate, let's take away the aggregation. Let's replace the group by an order by, just so we can see the data that we're working on. And run the query, and we see that student 123 has 4 applications to Stanford, Berkeley, and Cornell, 3 distinct colleges. 234 has 1, and so forth. So now let's return to our original query, group by student. We'll count the distinct college names. Run the query, and we get the expected answer. Student 123 applied to 3 distinct colleges, 234 to 1, and so forth. Maybe we'd like to have the student's name in the result as well. That's easy to do. We just add the student name to the select clause, and we run the query, and now we've added Amy is 123, Bob is 234, and so forth. That worked out fine in this case, but we're going to see in a moment where simply adding an attribute to the select clause in the case of a group by does something a little strange. In fact, the only reason that it worked nicely in this case is that when we group by the student ID, within each group, we have the same student name. Let's see that. Let's just take a look at that. Again, we'll replace the group by with an order by. We're sorting by student ID, and we see for the first group, which is 123, we have all Amy's. For the 345 group, we have all Craig's, and so on. So when we put student name in the select clause for our group by query, it was okay because for each group, we had the same name of the student. When that's not the case, we should presumably get an error, but let's see what happens. So let's say that we're interested now not only in finding the student name in our query, but we're further going to add a college name. So let's go back to the original query, distinct college name. Let's add college name in our result, and let's go back to grouping by student. So now for each student, we're going to return for each group, which is identified by the student ID, we're going to return the ID, the name, the number of distinct colleges, and then a college. Let's run the query, and we do get a result. We don't get an error. So we've got Amy, 123. She applied to 3 distinct colleges, but for whatever reason, the system decided to tell us about Stanford. Craig applied to 2 colleges, and the system tells us about MIT. Let's go back again, revert now to our order by form of this query, and take away the aggregation. And when we run the query, we see there's Amy, and she did apply to 4 different colleges, but when we put the college name in the grouping query, it chose to tell us about Stanford. What this system is actually doing is when we include in the select clause of a grouping query, again, if we go back to group by, and we put in the select clause an attribute that's not one of the grouping attributes, it actually chooses a random value from the group to include. In the case of the student name, the random value is always the same because the student name is always the same for the same student ID. In the case of the college, it chose a random value among the colleges. I personally am not crazy about this behavior. Among the 3 open source database systems that we've been using for our demos, 2 of them allow this behavior, SQL-Lite and MySQL. I happen to be using MySQL today. If we were using Postgres, it would actually throw an error in this case. Let's go back to the original query that finds the number of colleges applied to by each student. Here it is as we originally wrote it, and here's the result. Now, there may be some students in the database who haven't applied to any college at all, and they're not going to be represented in our result because they're not going to be in the result of the join, and we don't see any 0 counts here. What if we wanted to actually list the student IDs of students who haven't applied anywhere and include a 0 in the result? This is actually one of my favorite queries to give as an exercise or an exam question in my class because it takes a little innovation to figure out how to write it. The way we write it actually is by using the union operator, which I hope you remember from a previous video. We're going to take the union of the students who have applied somewhere and the number of places they've applied together with the students who haven't applied anywhere, and for those students we're going to put a 0 in the result directly. So let me just write the beginnings of this. So we're going to find those students who haven't applied anywhere at all. So those are the students whose SID is not in at all the set of SIDs in the apply relation. So that finds the students who didn't apply anywhere. For each student, we'll return their student ID, and then we want to have a 0 in the result. Very simple to do. We simply write 0. We run the query, and now if we scroll down, we'll see that in addition to all the students who have applied somewhere, we get zeros in the result for the students who haven't applied anywhere. The last clause that we're going to introduce in this video is the having clause. And the having clause is also only used in conjunction with aggregation. What the having clause allows us to do is apply conditions to the result of aggregate functions. So the having clause is applied after the group by clause, and it allows us to check conditions that involve the entire group. In contrast, the where clause applies to one tuple at a time. So this particular query is finding colleges that have fewer than 5 applicants. So we look at the apply relation, we group it by college name, so we're going to have one group for each college. Then we're only going to keep those groups where the number of tuples in the group is less than 5, indicating that we have fewer than 5 applicants to the college. We'll run the query, and we'll see that Berkeley and MIT each have fewer than 5 applicants. So presumably Cornell and Stanford have greater than or equal to 5 applicants, and you can check that by examining the data. Now, it is possible to write this same query without the having clause, and in fact without the grouping clause. And let me show you how that's done. We're going to select again the CNAME from apply, and here's what we're going to do. We're going to add an attribute there. We're going to, a table variable. We're going to erase this whole business, and we're going to find all applicants, so all applications where, let me just type this out for you. 5 is greater than the count from apply A2, where A2.CNAME equals A1.CNAME. And let's take a look at what this is doing. So what we're doing here is we're looking at each application record, and we're checking whether the number of other applications to the same college, we're going to find all the applications to the same college, we're going to count them, and we're going to see if that number is less than 5. So it's a little bit non-intuitive. Now remember, the result should be Berkeley, MIT. Let's run the query, and we do get Berkeley, MIT. We again get duplicates, however. The reason is that we're running this, we're checking this condition for each application record. So for each application to Berkeley, we check the condition. There may be many of them, and for each one to MIT, and so on. Of course, as usual, we can add distinct. We can run the query, and now we get the result. It does happen, actually, that every query that can be written with a group by and a having clause can be written in another form. Sometimes it can be extremely contorted, but another sort of complicated exercise I like to give sometimes in my class is to prove the fact that you can write every group by having query without using those clauses. Now let's go back to our original form of the query where we use the group by and the having. So we'll just get rid of all this. I'm sorry, I'm such a terrible typist. Group by college name, having count star less than 5. And we'll run the query, we'll get the same result. What if we were interested not in those colleges that have fewer than 5 applications, but rather those colleges that have fewer than 5 applicants? It's a subtle point, but instead of counting the number of apply tuples for each college, what we want to count is the number of distinct student IDs that appear in the group of apply tuples for that college. So again, now we're looking for the number of colleges who have fewer than 5 distinct people, distinct students applying to them, and now we see that one more college joins the group. So Cornell had more than 5 applications, or at least 5 applications, but it has fewer than 5 applicants. Here's our grand finale query. It has a having clause and group by, and in addition it has a subquery within the having clause that also uses aggregation. What this query finds is all majors represented in the database where the maximum GPA of a student applying for that major is lower than the average GPA in the database. So we join student and apply, and we group by the major so we can look at each major one at a time. Within the major, we find the maximum GPA of a student applying for that major, and we check whether it's lower than the average GPA in the student relation. We run the query, and we discover that bioengineering and psychology, at this point in time, are garnering applicants whose highest GPA is lower than the average in the database. Of course, that does not represent reality.